Somewhere in the universe right now, a cloud of hydrogen gas is collapsing under its own weight, heating up, and preparing to ignite a nuclear furnace that will burn for billions of years. The process that transforms a cold, drifting cloud into a blazing star is deceptively simple. Pile enough matter together, and gravity will do the rest. Below about 13 Jupiter masses, an object remains a glorified gas ball, silently drifting through space. Above that line, something remarkable happens. Deuterium, a heavier isotope of hydrogen, begins to fuse, releasing a faint glow. These brown dwarfs occupy a strange middle ground, too massive to be planets but too lightweight to sustain the full hydrogen to helium fusion that defines a true star. They range from roughly 13 to 80 times Jupiter's mass. Intriguingly, packing more mass onto a brown dwarf barely changes its size. Instead, its interior simply grows denser, raising core pressure just enough to spark slow deuterium fusion reactions. In 2025, astronomers using the James Webb Space Telescope proposed an entirely new spectral class, H, after discovering ultra-low-mass brown dwarfs in the star-forming region, IC 348, that display an unidentified hydrocarbon absorption signature previously seen only in the atmospheres of Saturn and its moon Titan. The JWST has also detected the first brown dwarf candidates outside the Milky Way, in the star cluster NGC 602 within the Small Magellanic Cloud, roughly 200,000 light-years from Earth. These discoveries are rewriting the boundary between failed stars and true ones. Cross the 8-0, Jupiter, mass threshold and hydrogen fusion ignites in earnest, birthing a main sequence star. The smallest of these true stars are red dwarfs, barely massive enough to sustain the reaction that converts hydrogen into helium. They constitute an estimated 70 to 80% of all stars in the universe. Because their interiors are fully convective, meaning hot plasma constantly circulates from core to surface and back, red dwarfs can access and burn virtually all of their hydrogen fuel. The result is staggering. A red dwarf with 1/10 the Sun's mass could burn for 10 trillion years, roughly 700 times the current age of the universe. No red dwarf has ever died of old age. The universe is simply too young. Every red dwarf that has ever ignited is still burning today, fizzling along at a fraction of the Sun's luminosity. Barnard's star, one of Earth's closest stellar neighbors at just 6 light-years away, is a red dwarf so dim it remains invisible without a telescope. When red dwarfs do eventually exhaust their fuel trillions of years from now, they will not swell into red giants like more massive stars. Instead, they will slowly shrink and heat up, transitioning into theoretical objects called blue dwarfs. A star like the Sun, 7 times more massive than Barnard's star, but nearly 300 times brighter with twice the surface temperature, will exhaust its core hydrogen in about 10 billion years. Small changes in stellar mass produce enormous differences in brightness and longevity. Here is where stellar science delivers its most surprising twist. Common sense suggests that the most massive star should also be the largest, but that is spectacularly wrong. R13601, located 163,000 light-years away in the Tarantula Nebula of the Large Magellanic Cloud, holds the title of the most massive known star. Current estimates place its mass at roughly 250 to 290 solar masses, and it radiates over 7 million times the Sun's luminosity. Yet despite this jaw-dropping output, R13601 spans only about 30 to 40 times the Sun's radius. It is a furnace of almost incomprehensible power packed into a surprisingly compact frame. The star burns so furiously that it is literally tearing itself apart, losing mass through stellar winds at a rate that beggars belief. The theoretical mass limit for star formation sits around 150 solar masses, beyond which outward radiation pressure from the core should blow away any additional infalling gas. Stars like R13601 likely formed through the merger of multiple massive stars in extraordinarily dense stellar nurseries. They burn through their core hydrogen in just a few million years, making them cosmically short-lived. The upper boundary of stellar mass is not a hard wall, but a soft limit that nature can circumvent under extreme conditions. The path to true enormity lies not in accumulating more mass, but in stellar death. When a main sequence star begins exhausting the hydrogen in its core, the core contracts, heats up, and drives faster fusion reactions that push the outer layers outward in a dramatic swelling called the giant phase. A star only 30% more massive than the Sun, like a crux, has ballooned to 84 times the Sun's radius. The Sun itself will one day expand to roughly 200 times its current size, engulfing Mercury, Venus, and possibly Earth. Blue hypergiants like the Pistol Star, at 25 solar masses and 300 solar radii, radiate intense blue starlight and live only a few million years. Yellow hypergiants, such as Cassiopeia, stretch to 500 solar radii and blaze with 500,000 times the Sun's luminosity. Only about 15 yellow hypergiants are known, suggesting they represent a brief transitional state between other phases. Then come the red hypergiants, the largest stars confirmed to exist. The current record holder is Stephenson 2-18, a red hypergiant in the constellation Scutum roughly 19,000 light-years from Earth. Its estimated radius of 2,150 solar radii means that if it replaced the Sun, its surface would extend past Saturn's orbit. Light itself would need 8.7 hours to circle Stephenson 2-18 once. Its volume is approximately 10 billion times that of the Sunday. The fastest plane on Earth would take around 500 years to make the trip. Stephenson 2-18's surface temperature hovers around 3,200 Kelvin, cool by stellar standards, giving it a deep reddish hue. Its estimated radius actually exceeds what current stellar evolution models predict as possible, since the theoretical upper limit for red supergiant size in the Milky Way sits around 1,500 solar radii. Tiny uncertainties in distance measurements, combined with the fact that these stars are literally blowing themselves apart through powerful stellar winds, make precise sizing extraordinarily difficult. Whether Stephenson 2-18 truly dwarfs all competitors, or whether updated measurements will crown a new champion, remains an open question. As Stephenson 2-18 continues to evolve, it will shed more mass, likely shrink into a hotter hypergiant phase, accumulate heavy elements in its core, and ultimately explode as a core collapse supernova. That explosion will scatter elements like carbon, oxygen, and iron back into the galaxy. This cycle of stellar birth, death, and rebirth is the engine that has enriched the universe with the chemical complexity necessary for rocky worlds and, eventually, life. Every calcium atom in human bones and every iron atom in human blood was forged inside a star that died billions of years ago. The largest stars in the universe are not just spectacular curiosities. They are the cosmic factories that make existence as complex beings possible. We love hearing from you, whether it's a question about stellar mass or a story about your first time looking through a telescope. Leave a comment below. Your discoveries are what make this community great. See you in the next video.